Welcome to Untuition. Let's talk about the Schrodinger equation today. If you have been studying quantum mechanics for a while, you must know that the Schrodinger equation is one of the most important equations in quantum mechanics, which can be applied to solve a variety of hypothetical and real problems. But have you ever thought how Schrodinger originally discovered his equation? Here is a simple explanation. Let's consider a single particle moving in the space with momentum p equal to m multiply velocity. In this case, the total energy of this particle is equal to its kinetic energy, half m v squared. Or if we use p, it became p squared divided by 2m. So this is a simple relation we can obtain in the particle model. On the other hand, in quantum mechanics, this particle can be described by a wave function or for a plane wave, psi x, t, the two variable, equal to a exponential I and the phase, the phi. Here phi represents the phase. Phi equal to 2 pi divided by lambda multiply x minus omega t. Now, here we know that there are two important formulas in quantum mechanics. One is Planck's formula for energy, E equal to h multiply f, the frequency. Alternatively, this formula can be rewritten as h bar multiply omega. The omega here, the two omega here are the same, the angular frequency, where h bar is simply h divided by 2 pi. The second important formula in quantum mechanics is due to de Broglie. That is P moment equal to h divided by lambda. If you just substituting these two basic equations into the phase formula, we can obtain that phase phi can be written as, can we put a 2 pi here, and we divide the h and immediately multiply the h. So in this way, we can obtain h over lambda multiply x. The second term, then omega can be simply written as the total energy divided by h bar and multiply t here. So the first term, the h over lambda is exactly the momentum. And if you divide the two, if you move the 2 pi in the denominator, we got h bar. So based on these results, we can rewrite the phase formula as 1 over h bar p multiply x minus e multiply the t. Okay, as we know that every fundamental equation in physics must be written as a differentiation equation. So here we are looking for differential equation behind this the wave function. And what can we do? First, we can work out the first derivative of the psi with respect to x. Here we can simply use the chain rule, delta psi, delta phi, multiply delta phi delta x. And the first term will be a multiply e I phi. And here we use the chain rule. The delta phi with respect to delta x is simply IP divided by h bar. That is the first derivative. Actually, it can be simplified as a factor IP divided by h bar multiply the psi, the wave function. Then let's go to the second partial derivative with respect to x. So delta psi is the second partial derivative. Can be written as, can we just put this factor in front? We got IP over h bar and the first derivative, psi and delta x. Okay. If we just use the result for the first derivative here, we simply got the factor IP divided by h bar square multiply psi, the wave function. Okay. This term seems a little bit strange, so we can manipulate this factor slightly. First of all, I square will be -1. So in this way, we obtained p square over h bar square. Okay. So what does the p square mean? Well, if you're looking for this formula, p square is proportional to the total energy. So therefore, if we just multiply, before we go, we have multiplied the wave function psi here. So what do? We just multiply 2m. And on both denominator and numerator, we will got p square divided by 2m. Because that's physical meaning is apparent, which represent the total energy of the particle. So in this way, we have that negative 2m, m is the mass of particle, divided by h square, and that will become E multiply psi, the wave function. Okay, we have to go as far as the second derivative with respect to x. Let's do partial derivative with respect to the time. Hopefully, we can find a link that can connect the two partial derivatives, and that would be our differential equation for the quantum mechanics, in quantum mechanics. So let's go to first derivative, delta psi, delta t. Again, we can apply a chain rule, that is delta psi, delta phi, multiply delta phi divided by delta t. Okay, the first term is just the wave function itself. And the second term, if we just use the formula for the phase, perhaps I need to highlight this formula for the phase because we use them again. And so you can see that, be careful this time, the negative sign must be taken into account in front of energy. So in this case, we will have the factor will be the I over h bar multiply the E and the negative sign. So this is factor. So can we put this factor in front of the wave function? That will become I over h bar and multiply E multiply the wave function. This is the ha-ha moment that you can see that there is a cofactor here appear in both partial derivative with respect to x and the partial derivative with respect to the time. So that is a link we are looking for. Before that, can we just rewrite these two partial derivative slightly? So for this one, I just multiply negative h bar square and divided 2m. In this way, we got a negative h bar square divided by 2m. And then we just write the original second derivative, dirt square and dirt x square, multiply the wave function psi. That is left-hand side. The right-hand side became simply as the E, the total energy, multiply psi, the wave function. Similarly, we can just move this factor to other side, and then we will multiply h bar and divided the I first. That is that will become first derivative with respect to time t. Okay, normally we just prefer to put this I in the denominator. So what we can do, we can multiply the I, and I squared became -1. So this negative and negative became positive. So eventually we will have I h bar, the first derivative of psi with respect to the time. And that is a left-hand side. The right-hand side will be identical to the product, E multiply psi. So just compare with these two equations, we can simply obtain the differential equation. This differential equation, that is left-hand side, is h multiply h bar as delta psi, delta t, equal to the left-hand, this right-hand side will be negative h bar square and 2m, and this is just partial, the second partial derivative notation, multiply psi. One moment. This should be 2. This be psi. This is the Schrodinger equation for the free particle in space. I just highlight this result here. So this is Schrodinger equation. Okay, it's not so difficult to obtain, as you can see. Of course, in general case, we have to generalize this left-hand side by taking into account of the potential energy. So we have to consider the total energy. So in general, E is equal to the sum of kinetic energy and the potential energy, EP. If they use a notation, if you use a operator notation, and we prefer to use Hamiltonian, which is represents the total energy, were equal to the kinetic energy will be equal to the h bar square and divided by 2m, and the operator is the second derivative, x squared. And for the potential energy, we simply use V for the potential energy as a function of x. So that would be our operators for the Hamiltonian. So in this way, we can actually generalize this partial differential equation into a Schrodinger equation as we used in the textbook, which is I multiply h bar partial derivative with respect to the time equal to negative h bar square divided by 2m, and the second partial derivative, delta square and delta x square, and multiply the wave function psi plus the potential energy V as a function of x multiply psi. So this is actually the formula of Schrodinger, or Schrodinger's formula, that was first discovered by Schrodinger in 1925. And this is rediscovery of the Schrodinger equation. I hope you enjoy this explanation. Thank you for your watching. Have a nice day and goodbye.